Hello, Mr. Hasty here. Today we're going to be talking about section 11.2, which is on the conservation of energy. And we just did a lab on this, kind of implying what we were going to be talking about today, and that is that the total energy of a system remains constant. So the law of conservation of energy says that in a closed, isolated system, so let's make sure we're good with that. We'll just finish this out. Energy cannot be created or destroyed. So, isolated means that everything that is in the system that we're considering is everything we need to do the problems. Closed means that we are not going to be losing any energy to something outside the system. So anything we need to take account for needs to be taken into account in the system. So one of the most common applications of this is the application of mechanical energy. Mechanical energy is really the sum of kinetic energy and potential energy. Now it could be different types of kinetic. We could have rotational kinetic or translational kinetic. We could have gravitational potential energy or elastic potential energy, but usually we work with gravitational and translational kinetic. Those are the most common. So a formula here is mechanical energy is just kinetic energy plus potential energy. Furthermore, to go along with the idea of the conservation of energy, the general formula is that the energy in the initial setup is equal to the energy in the final setup. So real quick, let's talk about how we lose energy when we talk about losing energy. In a closed, isolated system, you shouldn't lose energy if we've properly established what our system is. But in reality, we lose energy because no system that we work with in a practical sense is usually perfectly closed. So oftentimes kinetic energy is lost through friction or vibration. Okay. Friction is a form of thermal energy. Vibration is another form of kinetic energy. We can lose thermal energy due to light energy. When it creates light, it expends energy to do that. It can also lose thermal energy due to what's called thermal displacement. We lose electrical energy to resistance, which is a form of heat, and occasionally to light. But basically, the transfer of energy into a type of energy we don't really want is how we quote-unquote lose energy. So let's talk about visualizing an energy transfer real quick. So let's assume we have the ball on the ground and the ball gets kicked up in the air and comes back down. We're going to analyze this ball at 3 points in its path. So when the ball's first on the ground, it would have zero kinetic and zero gravitational potential energy. But let's assume that it's right as it is kicked. Right as it's kicked, it's going to have its highest kinetic energy and its lowest gravitational potential energy. At the top, it'll have its lowest kinetic energy. Its kinetic energy is actually zero, but it's going to have its highest gravitational potential energy. And then it returns to a state on the ground where it has its highest kinetic energy, not while it's sitting on the ground, but right as it hits the ground, and its lowest gravitational potential. Now we could also model a pendulum, and that pendulum would just be the opposite of this diagram. It starts with a high gravitational potential, gains the most kinetic at the bottom, and then is highest gravitational potential at the other end. But what about like a one-directional, what about something rolling down a hill? So has something here, something here, something here. So here, we're going to have a point where you have the highest GPE, but as it hasn't picked up speed yet, it's going to have its lowest kinetic energy. In the middle, we might have relatively even, at some point, gravitational potential energy and kinetic energy. Somewhere in the middle, they'll even out. At the bottom, you're going to have your lowest gravitational potential energy and, of course, your highest kinetic energy. That is why you move faster going down a hill. So let's move on to some examples of modeling this mathematically. So in this first example, we have an 8.50 kilogram object is dropped from a 12-meter building, lands on a platform that is 8 meters tall. So there's two ways to do this problem, and it is based on how do we set up our reference frame. So one option is to call the platform 0 and the roof then 4. The other option is to call the roof 12 and the platform 8. Either way will get you the same result numerically. Some of your work along the process will look different, but it'll work out either way. So let's go ahead and call this 0 and this height 4. So part A, it says determine the kinetic energy of this should be object, says lim, object, as it reaches the platform. So what this is it's a relationship between the gravitational potential and the kinetic energy. So at the beginning of this, it has 0 kinetic energy when it's first dropped and all of its gravitational potential. So let's start by figuring out what the initial gravitational potential energy is. It's going to be mgh, so that's 8.50 kilograms times 9.8 for gravity times a height of, in this system, 4 meters. Now, I'm not going to work that out yet. What we need to understand is the entire setup here. So in the beginning, we have gravitational potential energy initially, and we have kinetic energy initially. And that's supposed to be equal to the gravitational potential energy we have at the final plus the kinetic energy we have at the final. Now, how we've chosen to set up this system works out very nicely for us. Our initial kinetic energy is going to be called 0 because when we drop something, it has initial velocity of 0, meaning kinetic energy of 0. At the end, because our height is 0 in this model, our gravitational potential is going to be 0. So this equation boils down to the GPE initial is going to be equal to the kinetic energy final. So that means that 8.50 times 9.8 times 4.0, our gravitational potential energy, is going to be equal to our kinetic energy. Formula for kinetic energy is, well, actually it's just asking what the kinetic energy is, so we just need to do that calculation. And we get to 2 sig figs here, 330 joules of kinetic energy. Now this will allow us to establish part B, the speed it was traveling when it reached the platform. So formula for kinetic energy is 1/2 mv squared. And if we solve for v, that's going to be the square root of 2ke divided by m. Now our kinetic energy final is the 330, but that's a rounded value. I'm actually going to use what I got in the calculator, which is 333.2, and we will get 8.9 meters per second. All right, moving forward. A 300.0 gram ball is fired. Well, let's fix that real quick. So our mass is going to be, 0.3000 kilograms. Is fired into the air with an initial velocity of 22.5 0.0 meters per second. So part A says find the initial kinetic energy of the ball. All right, so formula for kinetic energy is 1/2 mv squared. And in this situation, that's going to be 1/2 times 0.3000 times 22.0 squared. Using a calculator, we get, with 3 sig figs, 72.6 joules, and that's actually exactly what I got. There's no rounding involved there. Part B, the height at which the ball will stop. Well, let's think about what that means. If we're firing a ball and it stops at the top, comes back down, this fits kind of that scenario we looked at earlier. At this point where we launched it, it had its highest kinetic energy, but it actually had 0 gravitational potential energy if we set our reference frame right there. If we know that here it has 0 kinetic energy, but it has its highest gravitational potential energy, we can use the initial kinetic energy to work out the gravitational potential energy. So using the similar setup as before, our kinetic energy initial is going to be equal to our gravitational potential energy final. So we've already worked out our kinetic energy initial. Let's plug in the information we know for our gravitational potential. So we have KEI, which is 72.6. I'm just going to write it as KEI, is equal to gravitational potential, which is mgh, m being 0.3000. I have too many zeros in that. Times the gravitational constant times the height, which is what we're looking for. So we simply solve for h here, and we will get a height of 25 meters to 2 sig figs. Or no, we have 3 sig figs here, so 24.7 meters. And that was rounded. Finally, the velocity of the ball when it is 10 meters high. So this is a little bit trickier because not everything is going to be as cut and dry here. So if we have our setup that kinetic energy initial plus gravitational potential energy initial equals kinetic energy final plus gravitational potential energy final. First of all, we've already established that the gravitational potential energy at the beginning is 0. So that's going to make that nice. We've already worked out the kinetic energy initial. What we're looking for is velocity. So we're looking for a piece of the formula for kinetic energy final. So let's fill in the information here. What the formulas are is 1/2 mv squared, vi, the initial velocity, plus 0, we're not going to put that in, equals 1/2 mv final squared, plus the mgh, and that'd be our final height. So I'm going to subscript f. I'm going to clear some of this so I can finish this problem out. So filling in known values, we're going to get 1/2 times the mass times the initial velocity squared, we already worked that out, is equal to 1/2 times the mass times the final velocity squared, that's what we're looking for, plus mgh. So the mass is 0.300, gravity's 9.8, and the height in this situation is 10.0. Now I'm going to work all this out algebraically and solve for v sub f. Just remember to be very, very careful as you do this on your calculator. Any rounding in the process will lead to an inaccurate answer, so you got to keep everything together without rounding until the very end. And to 3 sig figs, I get 4.06 meters per second. All right, let's move on to the final problem. All right, so this one's pretty tricky. A force of 15.0 newtons is applied over 3.00 meters to a 8.50 kilogram cylinder to roll it. How much kinetic energy does the cylinder initially have? Now, that doesn't... When you roll a cylinder, you actually end up getting two forms of kinetic energy. You end up getting a linear kinetic energy and a rotational kinetic energy, but it doesn't specify. It just wants the total kinetic energy. And then it wants us to figure out what is the linear kinetic energy and linear velocity, rotational kinetic energy and rotational velocity. That's going to be a bit of a dance with the equations there. So first of all, it's asking how much kinetic energy was given to it. Well, if you remember, we can use work. Work is equal to the change in energy. So we know that if it started at rest, it started with 0 energy. So basically, the amount of work we do is equal to our final energy. Now, work is calculated as force times distance. So we can say force times distance is equal to our final amount of energy, which is all kinetic. So in this case, it was a 15 Newton force, 15.0 Newton force applied over 3.00 meters. And so we get a total here with 3 sig figs of 45.0 joules. So our total energy done on this system is 45.0 joules. All right. Some of that is linear and some of that's kinetic. So we have to be able to figure out how much. So the first thing we're going to do, and we're going to kind of solve B and C at the same time, is we need to know that our total kinetic energy is going to be equal to our translational, which is linear kinetic energy, plus our rotational kinetic energy. Now we're going to work out some formulas for this. We know that our kinetic energy is already 45.0. So let's go and break out the formulas for kinetic energy translational. It's 1/2 mv squared plus, if we remember, kinetic energy rotational is 1/2 I for the moment of inertia times omega, which is the angular velocity squared. Now, if we look at this, we've actually got some decent information here. We know our kinetic energy, we know our mass, but we don't know any of our rotational information. And so what we're actually going to do is we're going to use what we know about moments of inertia and angular velocities to make this work out. So first of all, we have to look up what the moment of inertia for a cylinder would be. Remember, every shape has its own moment of inertia. The moment of inertia for a cylinder is 1/2 mr squared. Now, we definitely weren't given the radius, so that's going to be a trick here. So we're going to say 1/2 mv squared plus 1/2 times the quantity, 1/2 mr squared. The first 1/2 is just from the normal kinetic energy rotation formula. The other 1/2 is from the moment of inertia. So we also don't know anything about the angular velocity. So let's go back to a formula we do know about. Since we're already working with velocity, let's use the fact that the velocity of an object is equal to its angular velocity times its radius. So we can solve for this, and that means that omega is v divided by r. So I can replace this omega with v divided by r and square that. Now, when we simplify everything, we'll get 1/2 mv squared plus 1/4, 1/2 times 1/2, m. The radius squared here cancels with what's going to end up being a radius squared on bottom, and we just get v squared. These are like terms and can be combined to be 3/4 mv squared. Now, we know the mass, we're looking for velocity for part B, and we know our total kinetic energy of 45.0 joules. So we simply take 45.0 equals 3/4 times 8.50 v squared. And when you solve for v, that's going to be the square root of 4/3 of 45.0 divided by 8.50. And we get a velocity of 3 sig figs here, 2.66 meters per second. Now, to get the kinetic energy, then the translational kinetic, it says linear kinetic energy, linear velocity. We have linear velocity. To get the linear kinetic energy, we just have to go back to that formula, 1/2 mv squared, and we have to plug in the information. When we do that, we get exactly 30.0 by my calculation joules. Now, we could do a very complicated process for part C, but there's some nice little tricks here. We know that the total kinetic energy is 45.0 joules, and our translational or linear kinetic energy is 30.0 joules. That means that our rotational has to be the other part of that. Our rotational has to be 15.0 joules. So how can we figure out the rotational velocity then? Well, there's a couple different ways. We could use the fact that rotational velocity is v divided by r, but we don't know r. We could work out, try to use the formula for rotational kinetic energy, but we run into a barrier, and that basically comes down to the following. Without knowing the radius, we can't know the rotational velocity. So we take what we do know, the 15.0 joules, and that's all the information we can get. So we need more info if we want to find the rotational velocity. All right, that's it for this section. Hope to see you guys next time.